very happy to have our own Falk hustler to start us off the new semester. I, for one, am very intrigued to hear what he's been up to 2 doors down. So he's going to tell us about T-duality, integrable signal models, and supergravity.
Yeah, so first of all, let me say thank you for the guys to have me here as a postdoc. So it's a really nice place. It's awesome to be in Texas, and I really enjoyed a very nice food. So nice lunches together and so on. It's a great place to be here. And so what I want to do today is I want to tell you a little bit about things I'm interested in. So, and what I'm trying to do is, I really try to start with the basics. So I hope nobody gets bored, but I really, I do not want to show off, but I really want to give you some ideas which my work is based on. And I really want to make, or try to make clear why these things are interesting for me. And perhaps when you think they're interesting too, I would be very happy when we discuss us afterwards a little bit more. So, and in some sense, one very, very elementary point or ingredient of the things I'm working with is T-duality. So, and T-duality is probably known by everybody of you. So, and there, in some sense, the idea is that, of course, we know all Abelian T-dualities. So, this is what we probably hear in the first string theory class. And so, the idea is quite special to the string, because in contrast to a point particle, a closed string as an extended object can not only move along some direction, but it can also wrap around some non-contractible cycles. And this exactly will give us T-duality. So in some sense, it's a very, very stringy property. So, but there's another way you can approach T-duality from a more field theory point of view. And this is when you look at worldsheet theories and at sigma models. And so a famous approach was done by Buscher. And so what he did, he was just writing down a worldsheet sigma model for a target space which has some Abelian isometries, so like a torus or a circle. And then what he was doing there is, he was then introducing the gauge field, so he was gauging this symmetry of the sigma model, and he was also introducing a Lagrange multiplier. And then he was playing around a little bit with these two things, so he could either get rid of the gauge field, or he could get rid of the Lagrange multiplier, and so he was getting 2 duals in sigma models. And so they are exactly reproducing the story which you would also get, for example, from your CFT when you consider your critical string. So, but thinking about this gauging procedure is in some sense quite suggestive. Because of course, all you know that we not can only do Abelian gauge theories like electrodynamics. I mean, we also can do non-Abelian gauge theories. So that's why what people said is, okay, when we have this gauging procedure, we can also do non-Abelian T-duality. And so this is funny because I think not so many probably of you have heard about non-Abelian T-duality, so it's still something more special. And there is one simple reason why you have not heard so much about it. Because what you really have to do is, when you think about string theory, you have Riemann surfaces, right? So which represent your worldsheet. And so you do an expansion in the genus of Riemann surface. So for example, you start with a sphere, then you get a torus, and so on and so on and so on. And in some sense, this is like a little bit like the H-bar expansion you would do in quantum mechanics. So, and in string theory, you call this GS expansion. And the thing here is, so when you do this and you want to really globally well-defined doing this, so it's much, much easier for an Abelian gauge field on a torus, for example, to patch it in the right way than it is for a non-Abelian gauge field. So this is why people really have sometimes a problem with non-Abelian T-duality. For example, when you put it on a torus, you have problems of globally really writing down the gauge fields. And so that's why people normally say, this just works in the leading order of GS, so on the sphere everything is fine, but then it breaks down, and so that's why it's not a full symmetry of string theory, and we just threw it out of the window. But what I want to tell you today is that this is probably a little bit quick, and the funny thing is that recently people also noticed that, perhaps it was too fast. Because when I want to do, for example, the connection with supergravity, then I know that supergravity is 2 derivatives, so it's leading order in alpha prime, and it's also leading order in GS. And so as I will show you now is, when you think about supergravity, then non-Abelian T-duality perfectly makes sense. And in some sense, it's exactly at the same footing as normal Abelian T-duality. It just becomes more complicated when you think about alpha prime expansions or GS expansions. But even, yeah?
What is GS?
So this is the string coupling, right? So, and this exactly counts the genus expansion. So it's a little bit like the H bar, what you get in quantum theory. So this is in some sense the fine print which you have to think about when you hear non-Abelian T-duality. But there was another problem, which is probably a much bigger problem, because when you do the sketching procedure, then you will get another background. And when you do Abelian T-duality, you will get a torus from a torus, which is fine. But here, you will get a background which has some non-Abelian isometries, but the background you will get out after the dualizing does not come with this non-Abelian isometries anymore. So in some sense, you cannot do the same procedure again. You do not know how to get back. And this is really a problem because, I mean, it's called duality, not one-way street, right? So, I mean, duality means that you can go back and forth. But, so there's a very, very nice approach, and this is the one I will tell you today about, to resolve this problem. So this problem can be resolved because what people really figured out is that you have to do something which is called Pauseonly T-duality. And there you can cure this, this problem, because this problem just comes from not really using the right coordinates to describe the system. So you can cure this.
Sorry, could you please repeat what is the problem?
So the problem is, so when you do the procedure here, you start with a torus, you get another torus. So when you do the procedure here, you start with a space which has isometries, but you get another space which does not have isometries anymore. So you cannot do the same procedure to go back. Okay? So, and all those things are cured in some sense by Pauseonly, not the GS expansion problem, but the rest. And so that's why this is an interesting thing you should look at. But even more so, as I will tell you today, is that this Pauseonly is very, very closely connected to some problems in supergravity. And it's also very, very closely connected to some problems for integrable sigma models. So this is what we want to see. So in some sense, it's this kind of intersection between these blobs which makes it so interesting. And now that the funny thing is, so this was something which was just discovered recently, and so it still needs better understanding. But some very, very complicated problems, for example, in supergravity, are already solved in this language. I mean, they call it differently, they use different tools, but in some sense they face the same problem, and they found perhaps a clever way to solve it. So when you understand this interplay, you can take this problem and you can say to the supergravity people, hey, I now know how I solve your long-standing problem just by using techniques from here.
What kind of problems? Just
so for example, exactly. So for example, one thing is these consistent truncations. So I mean, there were some constructed explicitly, for example, by Chris and so on. But it's not completely clear how to construct all the consistent truncations.
Well, now we have exceptional theory machinery, so...
Exactly, and I will come to this point. Yeah. They, in some sense, trick you a little bit. Because what they tell you, they can tell you, I can construct for you consistent truncations, but you have to give me an object, which they call twist matrix. So when you can give me the twist matrix, I can construct everything you want. But the problem is they will not tell you what the twist matrix is. And to find the twist matrix, you have to solve some very, very complicated partial differential equations. And in general, you do not know how to do it. Understanding Pauseonly T-duality, I will show you, will immediately give you all the twist matrices. So this is exactly the thing. And I mean, so they call it different. For them, for example, that's the renormalizability of their sigma model. This is what these people would call a consistent truncation. And so there are all, and the nice thing is that it also works for integrable sigma models. So they call it differently, but you can map it to each other, and the problems are comparable.
So can one get a new supergravity out of this method?
I mean, when you say new supergravity, it's the same supergravity, right? I mean, you mean the background, the supergravity background, you mean, right? I mean, that's a solution to the supergravity field equation. So this you can get. But not really a new, I mean, so we are still doing string theory, right? We still have type 2A or type 2B, something.
Like, for example, Chris Hall get 2A star or something like that.
So
can one get
so there is one interesting thing is, so what people discuss, and so this is connected to integrable sigma models. So for integrable sigma models, people found out by looking at the Green-Schwarz string that you can have sigma models which have kappa symmetry. And for a very long time, people thought that kappa symmetry implies conformal symmetry. So this is what they normally thought. But what they figured out by looking at explicit examples, which were constructed for integrable models, that this is not the case. So kappa symmetry does not imply conformal symmetry. And so the problem there is then, what are the supergravity description, right? Because you know that the beta functions of supergravity give you conformal symmetry. And this is what's called generalized supergravity. And this is also what you will find explicitly in the language of Pauseonly. And also people were trying to write this down for exceptional field theory and so on. But this also comes out naturally. Okay, so, but let me start with Pauseonly T-duality. And so what I want to do in some sense is I really want to follow in some sense, the original discussion, so how it was invented. And so one way you can think about this is you think about conserved currents. So in a sigma model, and this is probably a very, very, very straightforward approach. So because you say I have a sigma model, and so I have an action, and so the action is just exactly the standard sigma model action. So something like you would like this, right? So that's a normal sigma model action. And so you have a metric and a B field, which you in some sense can put in one object. So which just combines your metric and your B field. So this is nothing fancy. And then of course what we also have is we have this axis here, and so these axes are in some sense just a map. So from the worldsheet, so this is just what I call the worldsheet, to some target space. And for us the target space is just G, which for me is a weak group. So this is just a weak group. So very, 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 very simple setup to start with.
The topology of G will not play a role for you?
Exactly. This is a very, very good question. So this is the only thing at the moment which plays a role for me. So it's just in some sense a topology of G.
So it does matter for you?
It does matter.
Okay.
It does matter, and we will see this later on.
Mm-hmm.
And so, but for me at the moment, metric and B field are completely arbitrary. So I can put every metric on it what I want and every B field, but just G sometimes in topology. And of course then, when I tell you about the conserved current, I want to look at the variation of the action. And of course, I have to tell you with respect to what I variate the action. And so this I want to vary with respect to this axis, so to the embedding. And I write my variation exactly in terms of two objects. So this E here, or this epsilon here, so this is just valued in the Lie algebra. So this is valued in the Lie algebra of G. So these in some sense are just the generators of G. And so this Lie algebra I also call small g. I try to write a mass frac, so I mean just not to confuse it with all the other g's are floating around. So this is a mass frac g. Okay, and then of course it's in the Lie algebra, but so this xi's here are in some sense right in the tangent space. So I have to connect this Lie algebra with the tangent space, and so that's why I use the fundamental vector fields. So these are fundamental vector fields. And you all know them. They are well defined on a group manifold. And so I can show that they have the following Lie bracket. So, and here they are left invariant. So I have to write this left invariant. And so when you do this every day, you also know that they come with a minus sign in front of the structure coefficients. And the right invariant would come with a plus sign. So there are these two choices. So that's it. So this is in some sense my definition of how I want to change my action. Very explicit. So, and when I do this, so then I get the variation of my action, and I can write it in terms of two parts. So for the first part, I just get a normal Lie derivative acting on this combination of metric and B field. So this is in some sense what one probably would expect. But so there is also another part, and so this is something which we will have a closer look at. So this other part has a current in it. So that's something like this. So, okay, what is this current? So I can give you explicitly an expression for this current.
What do you mean by interior product of VA on EIJ?
Oh, no. So this one here?
Yeah, what's that?
Lie
Lie
derivative.
derivative.
Oh, that's a lead derivative, sorry.
It's just the Lie, it's just the Lie derivative. So, and I can give you this current row, and I just write it for you to see that it splits in a quite interesting way. Because of course this current is a one form, right? So I have this part here, so involving metric and B field, and here I have one form on my worldsheet, and so no surprise, I also have another one form on my worldsheet. Okay, and so now you already see the splitting, and the splitting will be very, very important for what we will do next. So that's why I want to highlight it. So you have this part here, so which has that, and this is a chiral current in some sense. So this is chiral, and in some sense this has that bar, and this is anti-chiral. And again, this already comes a little bit into the direction of T-duality, right? Because you know that T-duality, because the string is an extended object, has a left-moving sector and a right-moving sector, and T-duality really treats this left-moving and right-moving sector differently. So this is how winding and momentum exchange happen. So this seems to be important, and we will see that it will. And so just to set notations, I call this J plus A and J minus A. So just for future reference. Okay. So, and now I was telling you I want to have conserved currents, and so in some sense you all know that conserved currents can be written like this. So this is the normal Noether procedure, right? So this would be a conserved current. So, but I mean, I'm not so fast here. So I want to allow a little bit more of generality. So that's why I introduced something which looks a little bit like the Maurer-Katan equation. So, and the reason why I'm allowed in some sense to do this is because this is in some way an integrability condition for the current. You know, I want to be able to integrate it. But you know in some sense also that on a group manifold, my real integrability condition is the Maurer-Katan equation. So I can also put this additional term, and this will be very, very important for us to really understand what is Pauseonly T-duality. And one thing I want to highlight here is that I get here some structure coefficients, right? Sorry?
Indices.
So, yeah, you're very good. So you spotted me making a mistake. So that's completely correct. So the point I wanted to make is so that these structure coefficients are different from these structure coefficients. So, I mean, so there's a priori no way to raise and lower the indices, so that's why they are different. And so they correspond to something which is called the dual Lie algebra.
The group not compact?
Very good point. In general, it does not have to be compact. So this can be everything. And so there's, for example, one already you hit this for non-Abelian T-duality. So non-Abelian T-duality is the simplest extension, right, of this picture. And for non-Abelian T-duality, this thing here is 0. So there, the dual Lie algebra is abelian, and the other thing is non-abelian. So, and this is funny because in this case, although this thing is non-compact, the other thing, for example, SU2 would be compact. So you can go from something compact to something non-compact. And so the dual Lie algebra I also call mathfrak G, and I just put a twiddle on it. So that's my notation. Okay, and so this is what called a non-commutative. conserved current. So, and this is normally when you ask people what is Pauseonly T-duality all about, then they will say non-commutative conserved currents. So, and now you exactly know the formal definition of this. But of course, now I want to show to you that this really makes sense. So, the first of all, what we have to of course say is
everything you've said so far simply follows from a sigma model on a group manifold.
exactly.
That's
exactly.
all.
Exactly.
No other input is used.
No other input. Exactly.
Okay.
And this will be also what I will
But
use.
the
for
sigma model happens to have the Zumino term. That's all. The B term field.
Exactly. It has to be. It has to be. But so
Other
that's
than that, it's just the usual
Exactly.
sigma model.
exactly. So that's quite general.
Okay.
Well,
Yeah.
okay, I'm still a little confused by something. So you're not yet assuming the lead derivative, you're not assuming at all the lead derivative annihilates EIJ.
No.
Right, so like that term, the term in the action, the lead derivative EIJ, I'm just now converting that to this, star J, wedge star J.
Very good. This is exactly what we will do now. So you have exactly the right thing, because I mean, so far what I want to do is I want to set this to 0, right? So
Right.
so this is how I connect exactly these two terms and make them talk to each other. So I set this one to 0, and then what you see is this term here has to compensate this term in
Right.
some sense, right? So what I then write down is, and this is a very important equation. So I have this constraint here. And so this is exactly what follows from your remark. So this is exactly what has to hold. And so this is what people call Pauseonly symmetry.
Where does that F come from?
This F here?
Yeah.
So this comes exactly from this relation.
Yeah, but aren't you going in circles now? You're trying to derive that relation.
No. I just say, this one is derived, right? So this one.
Why did you didn't write for me what L is? Why is L suddenly coming?
Oh, L is just the lead derivative.
But why is the structure constants now for the dual algebra?
I mean, this is just an ansatz, right? It's an ansatz. I say I want to find currents which fulfill this ansatz in some sense.
Could I phrase this differently? Could I say that, like, in the box equation, that I'm going to define capital F by that box equation? and the
Exactly.
content is capital F is a constant?
That's a way how you can think about it. So there are two things, and I mean we are not there yet. We have to do one additional step. So let me first say this is Pauseonly symmetry, because in some sense it's how defined. So first of all, what you really want to do is you want to integrate this equation, right? So here you have the lead derivative, and so there you have some partial derivatives in it, and you want to find an EIJ, which when I integrate it gives rise to some constants plus this part, which I know. And this is in some sense a very, very hard problem. And so one of the inventors of this thing once told me that when I will give you a metric and a B field, and I do not tell you anything more, even when it's Pauseonly symmetric, you will have a very, very hard to figure out whether it is or not. So the construction normally goes the other way around. So you start from some overlying structure, and then you will construct the metric and the B field in such a way that it solves exactly this equation. So that's the other way around. And this is exactly what we will do now. So, because this one still is, I mean, you see some structures and it was derived and you say you just want to find these currents. But of course this needs the metric and the B field to have a very, very special form. You know, I mean, it's not every metric and every B field which will fulfill this. And so that's why you call it Pauseonly symmetry.
And
Okay.
just to reiterate, just for everyone, like, so if I were just reducing now to a regular Abelian T-duality, I would say the lead derivative of Bij vanishes.
Yes.
And then, so J is both closed and co-closed.
Exactly.
Okay.
Exactly. This is and this is exactly in some sense the idea. So, and you can also get the Nonobediency T-duality and the more general set. So
Just so I understand what's being assumed. So if G were just a compact lead,
Yes.
then I would be able, then I would have a Cartan metric, and I can just make this out of that.
no. Exactly. That's the point. It's a very, very good point. So this is not, these indices are not raised and lowered by the Cartan metric. So these are completely different structure coefficients. They are completely unrelated, so far unrelated to these guys here.
So for fun, they're both called F.
Sorry?
For fun, they're both called F.
Call that
Yeah.
tilde.
I mean, so yes. I mean, I will, for you, I will call it F tilde. So the problem why I did not call it F tilde, they are objects in one bigger object, which is called F. So now you can unify them in one bigger object, which makes the whole discussion a lot easier. So let me do this. So you're a very careful crowd, so it's very good.
I just don't understand. I don't know what I mean by the
Yeah.
dual Lie algebra.
So
For any given Lie algebra G, is there not a universal standard way of defining a dual algebra?
very good question. We will come to this. It's very hard in general. Mathematicians have asked this question, and they have a classification because you cannot really, but we have to have one additional point to see why you can.
Is there at least a vanilla dual G algebra, vanilla variety?
Yeah, what you
which
always
are
can
guaranteed
the Abelian
each
one.
time you can.
The
No,
Abelian-
even non-abelian.
Nonobediency
No?
is more complicated.
Not even a canonical standard one.
There are some standards
Mhm.
which are important for integrable deformations.
Mhm.
But so let me tell you more of the story. So then I think it would be clear. Okay, so we have at the moment we have G and G twiddle, right? So this is something. Okay. So but then we have a little bit more. So because in some sense what we know is that we have this relation to hold. So we have this relation to hold, right? So, and of course, we can now apply another Lie derivative on this side here. And so then something interesting happened because we know that we can look at the commutator. So then we get these structure coefficients here mixed with these structure coefficients here. And this is really the important part. So what we will get is and I will not write it out completely. I will just give you the first two terms so you get an idea. So let me see. And also it's not really used very often because it's a horrible way to write it, but I still want to give you an idea that you can do it. Okay, and then it goes on. And in some sense, I think in general, you get 6 terms. So you get this structure here. And so this is interesting because what you will find is that you always have something which comes from G twiddle, which is combined with something which comes from G. And this is what people call, and I mean, I already heard the name, so this is what people call the Cocycle Condition. And this also comes now back to your question, because, I mean, you can give me a G and you can give me a G twiddle, so they both have to have the same dimensions, but in general they will not satisfy the Cocycle condition. And so mathematicians have, I think, give a classification up to 3-dimensional G's and 3-dimensional G twiddles.
So it is Diophantine type equations.
Sorry?
Diophantine equations, are they? I mean, meaning that there are integers involved and...
No.
No,
Okay,
they're
no.
not. Okay.
That's
Mm.
Okay, so...
Why is it even clear that it's unique?
It's not unique. That's a good thing. So, and I mean, in some sense, it's not unique. So, and we will use in some fact that
I
it's
think
not
the reason I'm
unique.
a little confused is, as a vector space, is a canonical dual. But
Exactly.
you're saying as a Lie algebra, they're
Exactly,
not.
exactly. You have an additional structure, which is the structure of the Lie algebra, where it's not. And so, I mean, so one thing when it becomes more clear is, so we can use something more elegant. And so this more elegant is, in some sense, we can now try to combine it into one object. So this is also what my notation was, in some sense, suggesting from the beginning. So I take a TA, and then I have the generators of TA and TA. So this generates G twiddle, this generates G. And now you also see the index structure, right? Because when I say, for example, TA, TB, then I get something like FABC, TC, and the other way around. So that's how the index structure comes by just writing it in this way. And then what I can find is that I of course now can also define something like this.
It has a plus sign, because here you have a minus sign.
So where's my sign? Oh, yeah. So there's a minus sign because so these are the left invariant ones, and so these are really vector fields. So, but these are just generators, right? And there you normally choose the plus sign, so because it's more convenient. So, of course, you can write something like this. And then the funny thing is, so first of all, we know that these are Lie algebra, this is a Lie algebra, and this is a Lie algebra. So this gives us sometimes like parts of the Jacobi identity of this bigger Lie algebra. But then this Jacobi identity for this bigger Lie algebra also gives us automatically the Cocycle condition. So that's why the easy way is to think as just coming from a big Lie algebra. And so, but you have to have something else. So this is not really sufficient. So you also have to have something like a pairing TA, TB. And this is something like AB. And so now the mathematicians come in and they say, so, and I just want to repeat this for you. So this guy here is HET invariant. So that means when I put the adjoint action on this generators, this guy will not change. And so it's non-degenerate. So, and this is this pairing here. And so for what am I using this pairing? So this pairing I'm using to identify what is called maximal isotropic subgroups. So I have my G and my G twiddle, remember? And so they are maximal isotropic. So, and the definition of maximal isotropic means just when I take their generators and plug them in this pairing, they have to vanish. So when I take the generator TA with TB, this is 0, and this is the same for TA and TB. So this is the definition of maximally isotropic. So that's why I also need this pairing at this point. So what does it buy me? So it buys me what's called a Lie bi-algebra, which at this point we just see as a very big or a double Lie algebra. And so this Lie bi-algebra I will call D. And so this is just G plus G twiddle. So this is the Lie bi-algebra. Okay, very good. So, and once we have accepted this part, I can now show you why this is really called Pauseonly.
So, do the other non-trivial parts, do both non-trivial parts of the Jacobi identity or the big T's follow from that equation that you wrote down?
Yes.
Okay.
Yeah, and so I mean, when you, in some sense, when you expand this guy, so what you also have to assume is that FABC and FABC, because, you know, when you really would expand the indices so that these guys are 0. So this is what you also will find in some sense. And then everything follows just from that Jacobi identity.
Is it the reason I'm asking is it looks like you wrote something like G and G tilde equal to 0, but there's a Jacobi identity piece which is...
Oh, sorry, but this is the pairing, right? Or, sorry, which one do you mean?
Top line, right?
So the top line, that's part of, if I wrote down the Jacobi identity for
Yeah.
the big F,
Yeah.
that's the part of that Jacobi identity involving G and G tilde.
Yeah.
And the part involving G and G is the original Jacobi identity.
Exactly.
What about the part involving just G tilde and G tilde?
It's the same. So I mean, this will be
Oh, it's the
also. It will be also because this is a subgroup, right? When you have G tilde and G tilde, it's it's a group. So I mean, then it's in some sense also trivial.
I mean, it will give you Jacobi identities of G tilde.
Yeah. I mean, so when you give me the Jacobi identity of the big group, you know, you will get the Jacobi identity of G. You will get the Jacobi identity
I
of
think
G.
I'm asking a stupider question. I'm just saying, I can view everything you did up until you wrote down the capital G as motivating its construction. So that equation, when you say, when you do this computation here in the box, upper below the box to get whatever is equal to 0, that motivates introducing this capital T. But that's only part of a big T's full Jacobi identity. And I'm just asking, where does the other piece of its Jacobi identity come from?
But I mean, so
Like if
there are 3 pieces in
Right.
Jacobi identity, right?
Yeah.
So there's a Jacobi identity for G in it.
Right.
There's a Jacobi identity for G twiddle in it.
Right.
And there's a Cocycle condition. There's not more. So one thing probably, I mean, so this is a technical point. So when you want to know it in full generalities, what you can do is you can lower this index in some sense with the eta matrix, and you will find that this is completely antisymmetric with respect to all these indices. So, and this is because this is at invariant. So this is what you can check. And then you will check that there are only 4 independent components. There is an independent component which is this. There is an independent component which is this. And there are these components here. And so they are 0. So that's why this is everything what is left. And so you will always get this identity there.
Okay.
So it's, I mean, we can, when at some point we can write it out, right? But so it's really
Just
old.
saying that the structure constants of one of the algebras is an invariant of the original algebra, essentially.
Yeah. Yeah.
G tilde structure is G invariant.
No, yeah, but I'm asking why is G tilde? Let's move on. I'll ask
Okay.
you later.
Okay. So what I now want to explain to you is why
Is
this
this
called-
Pauseonly algebra? The capital T is obeying? Or what?
Exactly. This
Is
is what we are doing now. So this is exactly because Lie bialgebra, in some sense, I will now show you how
Is it even a Lie algebra to begin with?
it's a Lie algebra. Yes, capital Lie is a Lie algebra.
Hmm.
It is. So what I now want to show you is, let me do it real quickly. So you know all the story about the Lie group, so a Lie group. So on the Lie group we have this kind of blob, and it's our Lie group G. And then at some point we have a unit element, so which I will call E. And then we have some functions, right? We can put some functions F1 and F2. And then of course I could put some vectors on this function. So this is V1, this is V2. And I know that these vectors in some sense span my tangent bundle, right? So this is in some sense T at the point E of G. So this is what we know. And then we also know in some sense that this is the same as our Lie algebra. So this is in some sense quite clear. So, but now what I want to do is I not just want to have a Lie group, but I want to have a Pauseonly group. So I want to have this Pauseonly group. So what do I need are Poisson brackets. So I have Poisson brackets, and so for example I can write down Poisson bracket F1 and F2. And so this is written in terms of some Poisson bivector. So this is a generic Poisson bracket, right? So and this is just a Poisson bivector pi. And so this Poisson bivector is not completely arbitrary. So the thing which it has to fulfill is some differential constraints, because this guy here fulfills the Jacobi identity, right? So get some constraints on that. Okay, so but how is this related to the story I've told you so far? For a Poisson-Lie group, there is an additional constraint. So, and the additional constraint is that when I take the derivative of this Poisson bracket with some functions, I mean, I just have 1 and 2, but I mean, you can have more, so it depends on the dimension of this group, of course, right? So, and when I evaluate this at the identity, as a unit element, so it's the same way as I did it here. So what you then get is you will get these structure coefficients. And this is exactly how you find the dual Lie algebra coming out of this construction. So, and that's why, in some sense, you can summarize this idea that when you combine these two things, so this Poisson-Lie, so what you will find is exactly this Lie bialgebra.
Why do the variance properties look backwards?
Sorry, again?
All of the variances look backwards. The indices are in the opposite places. Is that supposed to be true?
Oh, you mean this one here?
Yeah, I mean, the indices are in the wrong places.
Yeah, I mean, so when you really want to be very careful, so you see that these vectors here are dual to the one forms which you get. So you would have to flip the indices up and down. So, I mean, I did not do this because then it looks strange, but you're right. I mean, so, but the thing is really that this equation holds. And again, you should not think about it raising and lowering it with the Cotton matrix. It's just
That's
numbers.
right. That's why I want the variances to be
Yes.
the same.
Yeah, you can do it this way. So it looks a little bit strange having functions with other indices. So that's the only reason. So, but this is a Lie algebra, and so this is exactly as the identity. And so that's why the Pauseonly group, in some sense, exactly gives rise to this structure here. And so this structure here, in some sense, explains this equation here. And so that's why it's called Pauseonly T-duality. Okay, so but I'm a little bit too quick because so I have to explain to you why T-duality. Because so far what we really did is just Pauseonly non-commutative conserved currents, but why I'm calling it T-duality. So and to understand why it's called T-duality, we have to go back to the currents again. And so we have to remember that we have the chiral current and the non-chiral current. So what I really want to do now is to put a chiral structure on this Lie algebra.
I should think of G tilde as being canonically defined by the Poisson structure and G.
Yeah, that's one way how you can think about it. Yeah. Yes. So we want to have a chiral structure on D. So to, in some sense, formulate this also in this extended doubled language. And so the chiral structure in some sense can define as just a map which takes D and maps it to D. So that's what the chiral structure is doing. And you know, so for all these structures, when I want to split something in two parts, normally what I do is I said that this E should square to 1, because then its eigenvalues are +1 and -1. And these guys exactly come from the +1 and -1 eigenvector space. So that's in general how you do it. And so there's another consistency constraint which you have to put. So you also have to make this E compatible with the pairing. So otherwise you get problems at some point. So you impose this thing so that you can pull it from one side to the other side of the pairing. So that's all of it. And so once you have the E, so then what you can do is you can really define these currents. And I mean, I can now tell you what these currents are in this doubled notation. And the nice thing is that then things become much easier to understand.
Is that Kähler structure?
That's a very good question. Here at this point, yeah. So on the group manifold, it's always Kähler in some sense, and it's in some sense trivial Kähler when you have the right number of dimensions. You can do something more complicated. So when you are not just looking at group manifolds, G, but when you are looking at cosets, and then you can also get really Kähler, generalized Kähler, and all the stories. So, but I did not want to do it here because it's, I mean, so I just wanted to give the...
No, I just see an orthogonal structure and I see a symplectic structure.
Exactly. Exactly.
So,
exactly. And so, I mean, what you can always do here is you can get a para-emission structure. So, which in some sense, I mean, it's not a full Kähler structure, but this is exactly the mathematical structure what's given by these things. So, what I want to show you now is that you now can write down J plus and the J minus by simply, in some sense, using the projector. So you exactly use this thing, and you take a J, and so you project it to the chiral and the anti-chiral component, just the normal projector. And then, of course, I can write this thing down because it's on the double, right? So I have a J plus minus A plus this guy here. So this is just the decomposition, normal decomposition, and you see immediately this is the one we are interested in. And so this is exactly this guy here and this guy here. So this is in some way how I connect them. But what I did so far is in some sense a little bit tricking you, because of course I have to tell you what this guy is. So this is really the important part, right? Because to make a connection, I should tell you what all my objects are. And so this is in some sense where all the juice is included, because let me write it down. So this is also sometimes the most complicated part. So this is exactly how I define this current here. So, and now of course I have to explain you all the ingredients. So this guy we already know, right? So this is exactly our Poisson structure on the Pauseonly group. This is something you can look up in your favorite book about Poisson geometry. Then, so this guy here is the right invariant vector field. So that means when I take EA, BB, I get FA, B, C, BC. So this time without the minus sign. So that's in some sense the even nicer guy. So, and this is just the inverse transpose of this guy. So this is just the left invariant Nora-Paton form. And so that's it. So these guys we already know. So these are the coordinate decks, right? So this is what we know. And so then this P is just the canonical momentum. So the Pi is just the canonical momentum on the group. So, and I mean, so this is just what you get in order to write something like xi of sigma and pj of sigma prime, and this is what we probably all have seen in string theory course or somewhere else. So this is just a canonical circle. So in some sense what I was doing is I have this current J here, this complicated current J, and so I have this matrix here which just express it in terms of canonical variables. So that's in some sense the same. And so now the funny thing is, so for later reference I will call this thing here EAI. So because it will be important. But for the moment, so what I now can do is and I also indicated this here, I can now switch to an Hamiltonian formalism, right? So and in some sense, you know, so when you hear Pauseonly, you know, you have a Poisson bracket, so you have a Poisson structure, and always when you have Poisson brackets, in some sense it tries a little bit for a Hamiltonian formalism. And so this Hamiltonian formalism is called E-model. And so the E-model just tells you that you have Poisson brackets for this current. And so these Poisson brackets in some sense look like a Kac-Moody algebra. So you would really write down the Kac-Moody algebra on the Sprinfeld double. So this is a double thing. Sometimes also called Grimfeld, because this was the guy who invented this thing. So this is the current algebra which you get, and you can really rewrite it by just using this and then plugging this in. So, and then of course what you also need to have is a Hamiltonian. And the Hamiltonian also looks very simple. It's just the integral over the pairing of this J plus with J plus and J minus J minus. So that's it. So in some sense, this really condenses all the information about the sigma model I was giving you in the first place. So this is everything. And this is very nice because when you really would look at explicit realizations of metric and B fields, they look very, very complicated. They are highly nonlinear and so on. And I mean, you would never in some sense guess naively that you have such a nice and clean structure behind it. And so what you now can do is, so now in some sense we did the opposite way, right? We were starting from the sigma model and I was motivating for you how to get to these equations. But of course you could also start with these equations and you go down to the sigma model. So you can also do the opposite direction. And so what you would find is you would find here a sigma model on G, on the group G in some sense. So where you here in some sense have your group G, and so this is G, so I was drawing it there. And then you have your EAI, so which is the guy I've written down for you. And so in some sense, this EAI encodes all the information you need to go back and forth between these two ways of writing them. But what you also can do, and so this is a nice property of the Pauseonly group, so you can exchange G and G twiddle. So you can exchange them. And so, but in the end, you will still get the same double D group, right? It does not care whether you exchange them or not. But so when you exchange them, what you will get is then you will get a sigma model on G twiddle. And so the funny thing is what we were mentioning before, so I just tried to make this so this can be non-contact. So for example, this can be SU2 and this can be R3. And you get another EAI bar, which you construct in a similar way, but you choose another Poisson structure, another invariant vector fields. And so from this way of writing things, it's immediately clear that they are both identical, at least at the classical level. So, and this is what Pauseonly T-duality tells you. It tells you that you have at least two sigma models which can be related in such a way. And so the way how you can see it is exactly using, for example, the E-model. I mean, the E-model makes it manifest. So this is the idea. So are there any questions?
Well, again, more than two.
Exactly, very good point. In general, you can have more than two. So in general, you
Where
can.
in this procedure are you getting more than one?
So in general, all what really matters is D. So, and normally a mathematician play this game. You can now check in how many combinations you can split D. And there are some things where you have 4, 6, and so on. I mean, there are different ways to split it. So sometimes, I mean, so this is, that's the way you do it. And, okay, so now I have 5 minutes to tell you something about the rest. But I mean, so this is the most important part in some sense I wanted to communicate. So let's just do supergravity. So a little bit. Okay, so supergravity. And what I really want to tell you is something about consistent truncations. So, and in some sense, let me try to motivate consistent truncations a little bit. So, when I think about a field theory, I can think about it in the first approximation as some coupled harmonic oscillators. So, I couple them in some way. And I mean, it's a field theory, right? So I have an infinite number of them. So that's the way. So, and normally, of course, trying to solve such a problem is hard. And it gets harder the more degrees of freedom I have in general. So I mean, when I have classical mechanics and I do it as an undergrad, they normally give me systems with 1 degree of freedom or 2, but not with an infinite number of degrees of freedom. So that's why normally what people want to do is when I give you such a system, they want to ask, are there some subsectors of the system where I can decouple some of the degrees of freedom to make my life easier? So that's normally what you always do. And this is exactly what people in some sense call a consistent truncation. So people are hoping to decouple some of these degrees of freedom without affecting the other degrees of freedom. And one way you could formally do this, but this is a trick, so you could say you have here an M2, and you make it much, much, much bigger than M1. So then this guy will not move, and this guy is moving. And this is, for example, what you do for Kaluza-Klein reductions. So there you make the internal dimensions very, very small, so then the Kaluza-Klein modes become extremely heavy, and they decouple. But there are very, very important examples which are important for ADS-CFT where you cannot do this. So for example, when you have ADS5 cross S5, then you have the ADS radius in the same order than the S5 radius, and then you want to have your ADS big to do classical analysis there. So your S5 radius is big, and then all the Kaluza-Klein modes drop on you, and in general you could not do anything. But the miracle occurs, and so sometimes that's a miracle, so you can still find a sector of things which decouple. And so, I mean, there was this very nice work by Chris, I think, who pioneered these things. And so it's very, very hard to find these degrees. So, I mean, you have to have a lot of intuition, and so you have to have very high nonlinear Ansätze. But so more recently, and I mean, I think Chris was just writing it down and it works, so, which is very impressive. But recently, I mean, people were trying to do a more constructive way of getting these consistent truncations. So, and the idea behind this is that they use generalized geometry. So they use generalized geometry. And there the idea is in some sense that they have something which is called a generalized Lie derivative. And so this generalized Lie derivative, in some sense, is like the Lie derivative we have seen before, but on steroids. So we have a normal Lie derivative in here, and let me just write it down and then explain to you what it is. So this is what we would write for generalized Lie derivative. And so now what you can say is you have this U, and this U is a generalized vector. Everything is generalized, and so this has a vector in it, and it has a one form in it. So this is a vector, it lives in the tangent bundle, and this is a one form, which lives in the dual to the tangent bundle, right? And so this thing here combines these two objects. So it combines vectors with one forms. So why should we do this? So the answer why we should do it is because, so this combines diffeomorphisms, because we know that the normal Lie derivative is connected to changes of coordinates, so these are diffeomorphisms. But we also know that we have some gauge transformations, so gauge transformations. And here, for example, we have the B field. And of course,
sorry to interrupt. Tell me the second term in your generalized Lie derivative.
so this is the second term.
What is that?
So it's a Lie derivative on the one form.
The one form?
Yeah, so this is the one form, right? So
V looks like the vector. You wrote V.
no, it's a nu. Sorry.
Oh,
So
okay.
you have problems to decode my. So I use Greek. I use Greek for forms,
You.
and I use Latin for things. So it's probably a bad
Sorry,
notation.
okay, I understand.
Okay.
It looks like you wrote the Lie derivative twice.
No. That would be stupid. So okay. So we have the gauge field here, and so we know, right, that we have B goes to dA plus B as a gauge transformation, right? So this A would be a gauge transformation for the B field, and this is exactly why we introduce this form. So in some sense, we combine or we geometrize gauge transformations and diffeomorphisms.
So you have a capital V, which is a little v plus a mu.
Exactly.
And you have a capital
Exactly.
U, which is a little u plus a mu.
Exactly.
And in what sense is this generalized Lie derivative? Does it satisfy like all the properties of?
Yeah. And it's very nice. I mean, so in some sense, it satisfies all the properties, and you can really do a complete generalized geometry. That means so you can introduce a generalized metric. So for example, you have a generalized metric, and so you can write it down. And so the generalized metric in some sense combines the normal metric and the B field in a quite non-trivial way. So this is, for example, the generalized metric. And you see, so that goes the metric and the B field in, but they are mixed in quite a non-trivial way. And so this is important, and then you can calculate the generalized Riemann tensor and everything. So I mean, you can do things which you would do. And so now the nice way for this consistent truncations, now I have to give you a truncation Ansatz. And so this truncation Ansatz, which I now tell you, is exactly based on the guy we have figured out here. So this is really the truncation Ansatz. And so it tells me this generalized metric, and it tells me this generalized metric in terms of these E's, which sometimes are called generalized train fields, because in some sense they are like a train. So that's what you get. And so these guys here are just constant. And I mean, I erased it, but so remember, so on my first slide, I was giving you this condition where I said we have to integrate this. So with the Lie derivative on the acting on the E, so we have to integrate it. And these are exactly the integration constants of this process. So they're really the integration constants. So there are d squares there, where d is a dimension of the space-time here. And so that means I have d squared degrees of freedom. So you can see that here, this guy in general has an infinite number of degrees of freedom because I can expand it in Cocycle line modes. But here now only d square of them survive and they decouple completely from the rest.
It's symmetric.
It's symmetric, yeah. But so no, it has to be a, so you would normally say it's d,
Oh, t is times 2, okay, sorry. Yeah.
so you would normally say this, but then, I mean, there are some additional constraints on this guy, so that's why it's d squared. But that's a good question. So, and this is the truncation ansatz. So
The matrix is 2D by 2D.
exactly, the matrix is 2D by 2D, but from this 2D by 2D matrix, only d squared degrees of freedom survive. And so from this now you can read off your metric and your B field and everything. And I mean, people knew that this would be a consistent truncation. They do not know exactly what these objects are. So yeah. So shall we stop here, or shall I?
We should stop and thank the speaker, and then we
Okay.
should talk more after.
Okay. Yeah. Let's do this.
Are there any more questions before we start part 2? Just blurt them out.